Namaste. Welcome to my channel Qubit Educational Services. We have been solving the GATE XE paper 2007, the mathematics section, that is section A. This is our third video in that series. In the first two videos we have solved question number 1 to question number 14. We are going to start with question number 15 now. This is a question based on contour integration, a topic from complex variables. The problem is simple. It is based on the residue theorem. The problem reads, the value of the contour integral taken along the unit circle mod z equal to 1, so that is our contour or the path, cos hyperbolic z upon 4z squared plus 1 with respect to z is equal to 2 pi cos hi by 2, pi cos hi by 2, 0 and 2 pi I. To begin with, what we are going to do is, we are going to take this 4, that is coefficient of z squared, outside the integration. That is important. So if we do this, then the denominator, which is 4z squared plus 1, will get simplified to z squared plus 1 upon 4, and the 4 will sit here outside 1 upon 4. Now we can write this z squared plus 1 upon 4 as z squared minus I by 2 the whole square. Correct? We can write it that way. And the benefit is, now we can factorize z squared minus I by 2 bracket squared into z plus I by 2 into z minus I by 2 using a squared minus b squared formula. Once we do this, then we can determine the poles of the integrand, which means the values of z, the complex values of z, at which the function is not defined and therefore not analytic. And it's very simple. If you equate z plus I by 2 to 0, then you will get z as negative I by 2. If you equate z minus I by 2 to 0, then you will get z as plus I by 2. So that is very simple. The next part is to check which one of the two poles, or both of them, lie inside or outside mod z equal to 1. So what is their relative position with respect to our contour of integration? And it is very easy to check. If we determine, or if we try to find out the absolute value or the modulus of I by 2 or minus I by 2, then this will turn out to be half. It's very simple. Basic algebra of complex numbers. So that is 1 upon 2. Now this 1 upon 2 is less than 1, which means both the poles lie inside. Both the poles lie inside the contour C. Let's say I call this contour as C. So we need to consider the residue values or the residues at I by 2 and at negative I by 2 in order to evaluate this contour integral by residue theorem. So that is what we will do next. The residue theorem tells us that the value of the contour integral is equal to 2 pi I into bracket sum of the residues of the function, okay, sum of the residues of the function or integrand at all those poles which are inside the path of integration. And in our case we have both the zeros, right? Z equal to I by 2 and negative I by 2. The procedure of evaluating residues is very simple if we have poles of first order. What we do is, we substitute that particular value, that is, let's say z equal to I by 2, in the whole integrand except for that factor in the denominator which makes it 0. So in this case, for z equal to I by 2, z minus I by 2 is the factor which makes it 0. So just don't consider it. Don't substitute z equal to I by 2 here, because that will give you 0 in the denominator. So in the numerator it will be cos h of I by 2, and in the denominator it will be I by 2 plus I by 2. So that is 2 I by 2, and don't forget the 4 that we took outside initially. Similarly, if I take z as negative I by 2, I will substitute this z in the whole of the integrand except where it makes the denominator 0. In this case, that's the blue star, z plus I by 2. So it will be cos hyperbolic of negative I by 2 divided by negative I by 2 minus I by 2 or negative 2i by 2. So let me make appropriate colorings here. This is for I by 2 and this is for negative I by 2. Okay. Yes. So we can now evaluate this. But if we want to save time, then it would be good if we know the properties of cos hyperbolic. Just like the circular cos, or we just call it cosine function, cos hyperbolic is also an even function, which means cos hyperbolic of I by 2 and cos hyperbolic of negative I by 2, they both should give us the same value. That is a property of even functions, right? And what about everything else here? Everything else is identical except the negative sign that this function has here, or this term has here, which automatically makes the sum inside 0, and therefore the integral is 0. So the option is C. But if you want a more detailed explanation to this, then we have to recall the definition of hyperbolic cos. What is that? The definition of hyperbolic cos is cos h of z is equal to e raised to z plus e raised to negative z upon 2. And rather, this is now clear. This is now making it clear that cos hyperbolic of z is indeed an even function. It is indeed an even function. But nonetheless, if you want to continue it, continue simplifying it, the first step will be taking 4 common and I common from the denominator. So 2 pi I into 1 upon 4i cos h I by 2 minus cos h negative I by 2. Just apply the definition. In the first case, z will be I by 2. In the second case, z will be negative I by 2, but that is not going to make any difference because we have an addition sign here. Okay, we have an addition sign here. So for sine hyperbolic, the situation would have been different. Okay. So yeah, so that will give us 0 in the denominator, in the bracket, and therefore the whole integral is also equal to 0. Now I want to tell you one more thing about this problem. If you remember the Cauchy's integral theorem, it tells us that if f of z is analytic, okay, if f of z is analytic on and inside some contour of integration, then the integral of f of z along that closed contour C is equal to 0. This is Cauchy's integral theorem, we know that. But the converse of the Cauchy's integral theorem is not true, not always true, and the question 15 that we have solved just now is a proof of that. So we have got a function, or the integrand here, that is f of z, whose integral or whose integration along the unit circle mod z equal to 1 is 0. But is it analytic? No, it's not analytic, because it has two poles, z equal to plus or minus I by 2, which are inside the contour, but still its value is 0. So Cauchy's integral theorem's converse is not necessarily true. So that is our learning from this example. What is that? Converse of Cauchy's integral theorem is not necessarily true. And that's the important part. Indirectly they may test you in the exam whether you know this fact, that converse of Cauchy's integral theorem is not necessarily true. So that was question 15. Now let us go to question number 16. Question 16. Let f of z or x plus iy be u plus iv. Let it be an analytic function defined on the complex plane satisfying 2u squared plus 3v squared equal to 1. Then f is a constant. F of z is kz for some non-zero real constant k. The real part of the function is cos x plus y by root 2, and d, the imaginary part, is sine of x minus y by root 3. Now can solve this problem using the condition given there, 2u squared plus 3v squared equal to 1, and the Cauchy-Riemann equations. But I'm not going to do that. I'm going to kind of look for a trivial solution or look for a solution by imagining or by guessing a function. So what I will do is I'll say let our function f of z be 0 plus I into 1 upon root 3 for all values of z. Okay, so this is our function. Let us see if it meets all the requirements here. Is it analytic? Well, of course, it is a constant function, so it has to be analytic. It's a constant function, so it has to be analytic. So this criterion is met. Now, does it satisfy the condition 2u squared plus 3v squared equal to 1? Let us see. For our function u is 0 and v is 1 by root 3, mind you, it is not I by root 3. The imaginary part is real. You know that, okay, from the basics of complex numbers. So what will be the value of 2u squared plus 3v squared? It will be 2 into 0 squared, so 0, plus 3 into 1 by root 3 squared, so 1 by 3, so that is 1. So this requirement is also met. And we know that in this examination, at least for this question, it has only one correct option. So what's the answer? The answer is f is a constant. F is a constant. So the correct option is A. Now the other way to solve the problem could be to check for all the options and to arrive at the conclusions that only A satisfies the requirements. If it is a function of the kind k into z, it will not satisfy that, both the requirements, and same thing applies to C and D. So the correct option is A, f is a constant, because it meets all the requirements and also satisfies the conditions. Okay, so that is question 16. If you remember, in one of our previous videos from the same paper, say a question was there which we solved by making an appropriate choice of the function. Let me show that to you. What that problem was. Yeah, this was the problem. So we chose here the function f of x as a constant function again, which was satisfying all the requirements, and we arrived at the result almost immediately. So whenever possible, you try to figure out whether you can solve the problem by bypassing the usual way and arriving at the answer in a smarter way. Okay, let us go to question 17th now, which is a question on Green's theorem from vector calculus. The value of the contour integral xy squared plus 2x dx plus x squared y plus 4x dy along the circle C given by x squared plus y squared equal to 4 in the anti-clockwise direction is. This is a typical problem on Green's theorem. Of course, we are not going to evaluate this contour integral. Instead, we will evaluate its equivalent double integral. First of all, we will write it in our usual notations. So xy squared plus 2x will be u, and x squared y plus 4x will be v. Now what is the Green's theorem? The Green's theorem tells us that this integral, which is what we want, is actually the surface integral of, it's actually the curl of this function, curl of ui plus vj, right? And well, we know, because it is a two-dimensional function, its curl is going to be along the z-axis, and same is the situation with the area, any area if you take, be it an elementary area dx dy in the xy plane. Okay, so when if I take it as dot, let's say dA bar, that dA bar is actually dAi cap or dAk cap. Okay, so that dot product gives you 1, k dot k is 1. So what remains is just the scalar function partial v by partial x minus partial u by partial y. Now what is partial v by partial x? Partial v by partial x will be 2xy plus 4. And what is partial u by partial y? Partial u by partial y, there is no y here, so that will not participate in the differentiation, and it will be xy squared, so x into 2y or 2xy. So 2xy goes, so it will be 4. Now we know if we have a constant as our integrand in any double integration problem, then that constant comes outside, and then the value of the remaining double integral is basically area enclosed by that particular curve. So in this case, that particular curve is circle, x squared plus y squared equal to 4, isn't it? So what is the radius? Radius is 2, area is pi r squared, pi into 2 squared, so the value is 4 pi into 2 squared, 16 pi, option D. It's a fairly simple question, but again, what are the two things that you should know here? The first and the most important is you should know the Green's theorem. You should know the Green's theorem, and second, you should also know from your basics of coordinate geometry how to determine the radius of the circle x squared plus y squared equal to 4. It is not 4, it is 2. So it is 4 pi into 2 squared or 16 pi. Question 18, again a question on multiple integrals. The volume of the prism whose base is the triangle in the xy plane bounded by the x-axis and lines y equal to x and x equal to 2, and whose top lies in the plane z equal to 5 minus x minus y is 2, 4, 6 and 10. Now this is actually a direct application of the fact that just like a single integral represents area under a curve, the double integral is going to represent volume under a surface. Okay, volume under a surface. What volume are we supposed to find? It's volume of the prism. What is the top surface? They're saying here whose top lies in the plane z equal to 5 minus x minus y. So just like in our single variable integration, the integral of y with respect to x gives us area. In this case, the double integral of z is going to give us volume. Should not forget that. If you open any standard calculus like Stewart or Thomas calculus, then you'll actually find very nice visual representations of how the double integral actually gives us the volume. That's integration basically. Okay, so we know the z, we know the integrand, that is 5 minus x minus y. Now let us talk about limits. Limits are again very simple. They have given us the x-axis, the lines y equal to x and x equal to 2. Okay? So double integral as a volume is single integral as area. That's what I was talking about. Okay. Now we wish to represent this region using the boundaries, using its boundaries. Okay. Let us choose x as our outer variable of integration. So the limits on x will be x equal to 0, the y-axis, and x equal to 2. X equal to 0 to x equal to 2. Now to get the limits on y, we imagine a line being drawn parallel to y-axis. Okay, where does this line meet our region? First, it is y equal to 0, that is our x-axis. So the lower limit will be y equal to 0. Now while leaving the region of integration, our pink line is going to meet the line y equal to x, the blue line y equal to x. So we have to now make use of this boundary equation to get y, but luckily here y itself is in terms of x, y is equal to x rather. So the upper limit will be x. Okay, the upper limit will be x. So we now have everything. We now have everything that we need to proceed. So we can now integrate this. For those of you who know how to handle these integrals, that this is going to be just a simple integration problem. But in case if you don't know, or if you have forgotten a few things, here is how we approach it. Whenever we are integrating it with respect to y first, we have to assume that everything involving x is a constant, just like in partial differentiation. So here that is the case. Y is the inner variable of integration, so we will be integrating this with respect to y first. So it will be 5y minus xy minus y squared by 2. And now let's go to the limits 0 to x. And once you do that, then you are supposed to integrate it with respect to x, but first we have to substitute these limits. Luckily the lower limit is 0, so it will be 5x minus x squared by 2. That's the new integrand with limits on x being 0 and 2. Now, during my days, we could evaluate this on our Casio calculators. Okay, but luckily or unluckily, you don't have that luxury, so you have to carefully integrate this. Okay, so let's combine x squared and x squared by 2 to make it 3 by 2 x squared. Integrate this, x's integral will be x squared by 2 and x squared's integral will be x cubed by 3. Again, lower limit is 0, so just substitute x as 2 in your integrated format. So it will be 5 into 4 by 2 minus 3 by 2 into x cubed by 3's integral will be 8 by 3, and if you calculate it, how much will it be? 2, so that is 10. In this case 3 gets cancelled, this is 2 cube, so 8 by 2 4 and minus 4 is 6 cubic units. The option is C. Yes, the option is C. Let's now go to question number 19, which is on partial differential equations. The general solution of x into z squared minus y squared partial z by partial x plus y into x squared minus z squared into partial z by partial y is equal to z into y squared minus x squared is, and we have 4 options a, b, c, d, and in all 4 of them we have implicit functions. But as you can see from the differential equation itself, we have partial derivatives of z, so we may say that z is the dependent variable and x and y are independent variables, but that is hardly required here. Now at first you have to note here that this differential equation, this partial differential equation belongs to a particular class of differential equations, partial differential equations, and their standard form is this: p into partial z by partial x plus q into partial z by partial y equal to r. This is the standard form. Now if p, q and r are functions of x, y and z, then we call it quasi-linear. Partial differential equation. And if p, q, r are functions of only x and y and not z, the dependent variable, then we call it linear. So this is just like dy by dx plus py equal to q, but there we have only one independent and one dependent variable, but here we have two independent variables, x and y, and the dependent variable is z. Correct? Now it can be proved, but we are not going to prove that. If you want the proof, then you can refer to B.S. Grewal. They have given the theory of this in their partial differential equations section in that book. So it can be proved that the solutions to this partial differential equation are actually solutions of this symmetric this symmetric ordinary differential equations: dx by p equal to dy by q equal to dz by r. Generally, when you study linear differential equations with higher order, then in the second part of that section you study such symmetric ordinary differential equations. Now you might be knowing the two methods to solve such differential equations. The first one is called as method of grouping. Whether you take any two out of the two times. So you can either take dx by p equal to dy by q, or dx by p equal to dz by r, or dy by q equal to dz by r. Okay, and then you get the ordinary derivatives and simplify. So that is called method of grouping. Generally, some simple pre-designed problems can be solved by method of grouping. Otherwise, you can solve it by the method of multipliers. So here, if you try doing that, then the method of grouping does not work, because if you have taken dx by p equal to dy by q, then it will be better if z goes from that, correct? But that doesn't happen here with any two of the three. So we have to start with the method of multipliers, And one good thing about this is that the functions, the coefficients, at least p, q and r, they show some kind of symmetry, like x and then z squared minus y squared and so on. So let's see how we can solve this symmetric differential equation using, or equations rather, using the method of multipliers. So I've rewritten the differential equation here, differential equations symmetric, and the first set of multipliers that I have chosen is x, y, z. Now you need practice to guess the multipliers. Sometimes the multipliers can also be scalars or functions like x, y, z, x squared, y squared, z squared, or even x, y, z, depends. So in this case I have found out that x, y, z works pretty well. So in this method of multipliers, what you do is, so you take this, you multiply it by x, so that makes it x dx, and in the denominator you also do the same thing, so it is x squared z squared minus x squared y squared. Okay, then you take the second one, you multiply the numerator and the denominator by y, and then you add the numerator to this, so that is y dy, and then you add the denominator to this, so that will be y squared x squared minus y squared z squared. And then finally you do the same thing with this. Okay, so the numerator will be z dz, and what about the denominator? Z squared y squared or y squared z squared minus z squared x squared. Okay, that is the properties of ratios which we have done here. Now if you add everything, you'll find that this is getting cancelled. X squared z squared is cancelled by negative x squared z squared, negative x squared y squared is cancelled by positive x squared y squared, and of course this is cancelled, so this is 0. Now can't have a non-zero numerator and 0 denominator, so it has to be an indeterminate form. So x dx plus y dy plus z dz is equal to 0. Now you can solve this, so you can integrate this to get x squared by 2 plus y squared by 2 plus z squared by 2 equal to some constant, let's say c1, or x squared plus y squared plus z squared equal to c1 prime. That is our first solution, x squared plus y squared plus z squared equal to c1 prime. This actually represents a family of spheres in the three-dimensional space. So we've got the first solution, and it so happens that there's no need to find the second solution, because in all these cases the second solution is x, y, z. The first solution itself is different, so it's option A, because that is the only one which has x squared plus y squared plus z squared, so that is option A. Now you may ask how to find the second one, x, y, z. Then this is how we do it. The second set of multipliers, which by observations are 1 upon x, 1 upon y and 1 upon z. So if you repeat the process, okay, the method of multipliers, 1 upon x plus 1 upon y plus 1 upon z, 1 upon x dx plus 1 upon y dy plus 1 upon z dz, again there the denominator is 0, because now you see that z squared minus y squared when added to x squared minus z squared gives us x squared minus y squared, because z squared go, and when that added to y squared minus x squared, everything else goes, so again you get a 0 here. So the numerator is 1 upon x plus 1 upon y, 1 upon x dx, I keep on forgetting dx, 1 upon x dx plus 1 upon y dy plus 1 upon z dz equal to 0, right? That has to be the case, it has to be an indeterminate form. So if you now integrate this, what will you get? You will get ln x plus ln y plus ln z equal to what? We know that it is a constant, so let's call it ln c2. Therefore x, y, z equal to c2. So the second solution is x, y, z equal to c2, and because the differential equation has an implicit solution, I have to write f of some function of x squared plus y squared plus z squared and x, y, z equal to 0. In B.S. Grewal, if you refer to similar problems, they also write the solution in the following form. They call the first function as u, and they call the second function as v, and then they say it can be v as g of u, or well, u as some other function of v, say h of v, or collectively you can say the implicit function of them itself. Okay, so that is question number 19. Let's go to question number 20. Choose a point uniformly distributed at random on the disk x squared plus y squared less than or equal to 1. Let the random variable x denote the distance of this point from the center of the disk, then the variance of x is. So here is our unit circle, and the thing is, the random variable that is given to us is we have to choose any point here, choose any point, and then you have to get the distance of that point from the center. That is going to be a random variable, right? Because we can pick our point anywhere inside the circle, and we are not giving any preference to any quadrant or any specific direction. So they're saying it's a uniformly distributed at random. Okay, uniformly distributed at random. And then we have to calculate the variance of that random variable, which is the distance of this point from the center of the disk. First thing, point 1, it is a uniform distribution. It is a uniform distribution. So the probability density function, in that case, the joint probability density function, I would say joint, because both x and y are independent of each other. So it's a joint PDF. It has to be 1 upon area, because if it is a uniformly distributed, if we are choosing the point anywhere from the location inside, by the very definition of probability density function, geometrically the total area should be equal to 1. Total area should be equal to 1. But what is the area of the circle? The area of the circle is pi, right? So the integral of the joint PDF should be equal to 1. So the function joint PDF has to be 1 upon pi. Okay, 1 upon pi. Please understand this. Which property have we used here? If you remember the theory of random variables, a single random variable, let's say, then for any function f of x to be a valid PDF, it should always be non-negative, and it should have this property, equal to 1. Correct? Now here we are not interested in the whole xy plane, rather we are interested only in the unit circle. Correct? So we must have double integral of our function f of x comma y with respect to dx dy equal to 1 over the unit circle A, right? Or unit circle A. So that's the reason we have to choose the PDF as 1 upon pi, because two things. First, the net value should be 1. Second, the point is uniformly distributed. The point is uniformly distributed, so it has to be 1 upon the area. Okay. Now, to determine the variance, what's the random variable? It is the distance of this point from the center of the disk. So what is the distance? It is root of x squared plus y squared. This is x. Yes, of course, that is x. Now, this can be a bit confusing. How are we going to find the random variable x's variance? Because we don't know its probability density function. We know this joint PDF, but that is definitely not of x. This is where the extra formula that we have from variance is useful, right? What is that? That formula is variance of x is equal to expected value of x squared minus square of the expected value. Might have studied this formula in 12th standard. So can we find expected value of x squared and expected value itself? Of course, expected value of x. Yes, we can find that. So we'll start with expected value of x. Expected value of x. What's the formula that we'll use here? Formula is simple. Formula is whatever your x is. Okay, whatever your x is, you just substitute it here and multiply it by the probability density function. That is 1 upon pi dx dy. Now this integral can be very easily evaluated using transformation to polar coordinates. Because it is a circle. So if you want, I'll explain this now. Transforming to polar coordinates, it's a unit circle, so theta will go from 0 to 2 pi and r will go from 0 to 1. Root of x squared plus y squared is nothing but r. Then using Jacobians, dx dy will be r dr d theta. Everything else will be the same. So if we evaluate this now, 1 upon pi outside, r into r squared, and then theta, for theta the integrand is 1. Okay, so 1 upon pi to 1 upon 3 into 2 pi, so that is 2 by 3. Pi will get cancelled, so that's 2 by 3. That's me, expected value. Now we can find the expected value of x squared. So in this case, where you had root of x squared plus y squared, now its square will come. Its square will come, correct? Again, you should transform this to polar, but now the integrand will be different. There will be one more power of r there. Previously it was what? It was r squared, right? Because this was r and this was the Jacobian r. And now it will be r cube, right? R squared and then this r Jacobian r. And this r squared is important because we are determining the expected value of x squared. So integral of r cube is r raised to 4 by 4, 1 upon pi as it is, and for theta it is again 2 pi. Okay, so pi gets cancelled, so this is 1 upon 2. And now let us go back to the formula that I wrote here. Variance of x is expected value of x squared minus square of the expected value. What is the expected value of x squared? Did we find it? Yes, that's 1 upon 2. That's 1 upon 2 here. And what is the expected value itself? That is 2 by 3. We found it out here. It's 2 by 3. Take care. That's 2 by 3 and we have to square it. Okay, remember you have to square it. And okay, if you forget to do that, we'll get a negative value of variance. And variance can never be negative, right? So it's 1 upon 2 minus 2 by 3 squared, that's 4 by 9. Simplify that, 9 minus 8 upon 18, that's 1 upon 2. So the option is C. So the option is C. 1 upon 18. Question 21 on numerical methods. If Runge-Kutta method of order 4 is used to solve the differential equation dy by dx is equal to f of x with the initial condition being y of 0 equal to 0 in the interval 0 to h with step size h, then y of h is equal to. So this is a formula based problem, but there is one thing that we should note here. Usually when we solve these differential equations of first order by numerical methods, the standard form that we take is dy by dx equal to f of x comma y. And here you should note the absence of y term on the right side. So the right side is just f of x. The next thing is we are required, or we are given the values of x naught and y naught. So here x naught is 0 and y naught is also 0. Okay, because they have given us y of 0 is equal to 0. Now here please understand that y is not f of x here. Y is the unknown function whose values we are estimating using numerical methods. F of x on the other hand is the derivative of y. It is the derivative of y. So once you understand the difference between y here and f of x in the same problem, then I think the rest of the problem is pretty simple. Conventionally we would take y equal to f of x, but here that is not the case. Okay, that is not the case. That would have been the case if y had been e raised to x. Okay, but anyways, so once you understand the things that are given to us in the usual notation of Runge-Kutta, then we can apply that. Okay, yes, so we begin. We first note that f of x comma y is equal to f of x in the problem, and now we start finding the values of k1, k2, k3 and k4. The formula for k1 is h into f of x naught y naught, and because x naught and y naught are both 0 and y naught is anyways not participating in the evaluation process, so k1 will be h into f of 0. Okay, k1 will be h into f of 0. What about k2? The formula for k2 is h into f of x naught plus h by 2 comma y naught plus k1 by 2. Again, y naught plus k1 by 2 is not going to play any role. X naught is 0, so k2 will be h into f of 0 plus h by 2 or f of h by 2 itself. Now for k3, because k2 has no role to play in deciding the value of k3 for this problem, Okay, the same formula which we used for k2 can be used for k3 with k1 being replaced by k2. Again, k3's value will be the same as that of k2, that is h into f of h by 2. Correct. Now what about k4? The value of k4 is h into f of x naught plus h comma y naught plus k3. Again, y naught plus k3 is not going to play any role, so it will be f of x naught plus h, or f of h, simply h into f of h. Now what is k? In the formula, y at h is given by y naught plus k. Correct, y naught plus k, or y at 0 k plus k. Now the formula for k is 1 upon 6 into k1 plus 2k2 plus 2k3 plus k4. So this is the weighted mean. K is the weighted mean of k1, k2, k3 and k4. Correct. Now we have got everything, so we'll say y of h is equal to y naught or y at 0 plus 1 upon 6 into k1, so h into f of 0, plus 2k2, 2 into f of h by 2, plus 2k3, again 2 into f of h by 2, and finally k4, that is h into f of h. Y naught is already 0, 1 upon 6 as it is. Take h common from all the terms. Okay, well, sorry, I have forgotten to write h here and here. Sorry, that's my mistake. Should have been 2h and then 2h into that. So if you take h common, it will be f of 0 plus 2 times f of h by 2 plus 2 times f of h by 2, so that 2 and this 2 will make it 4, and then finally this will be just f of h. So f of 0 plus 4 into f of h by 2 plus f of h. Okay, and do we have that option? Yes, that is option E. That is option. Correct. Now let us go to question 22, which is an interpolation problem. It may not be a part of your current syllabus, but nonetheless it's good to know interpolation methods. Okay, again, we are not going to solve this problem strictly by either Newton's or Lagrange's interpolation. We know that you can interpolate the polynomials using Newton's formula or Lagrange's formula. Okay, Newton's or Lagrange's. But what I have done is they have given us that there is a polynomial of degree 3. So let it be of the form ax cube plus bx squared plus cx plus d, and we need to find a, b, c, d, and for that we have 4 points: 0, 3, 113, 399 and 4, 187. Now the thing is, at 0 it is 3, correct? At 0 it is 3, so that directly gives me the d value as 3. And now I can use the other 3 pairs, 113, 399 and 487 to get a linear system of 3 equations and 3 unknowns. The unknowns are the same, a, b, c. How can I get the 3 equations? One each corresponding to 113, 399 and 4, 187. Okay, so I have written that in the matrix form, correct? And when this question was set, calculators were allowed. Casio calculators capable of solving the system of linear equations like this one. Okay, now this is a very old calculator. This is 991 MS. Nowadays they use the 991 ES plus, and there is one more calculator name I forgot. Okay, well, I don't exactly remember the name of that calculator, but it is an updated version of 991 ES. But anyways, the point is you can actually plug in the augmented matrix in the calculator mode of linear equations and solve to get the values of a, b and c. So if you do that, you get the values of a, b, c as 1, 7 and 2. Of course, the actual way of solving these problems is using Newton's or Lagrange's interpolation formula, whichever is convenient to you. Okay, fine. So next is very simple. They have asked us to calculate the value of the function at 2. So I'll substitute x as 2. So it will be ax cube 1 into 8 plus bx squared 7 into 4 plus cx 4 plus t. So 8 plus 28 plus 4 plus 3, 4 plus 3 7, 7 plus 28 is 35, 35 plus 8 43. So f of 2 is 43. That is option C. Okay, so in this video we began solving the questions from question number 15 and we will stop at question 22. Question number 23 to question number 28 we will cover that in the last part of this lecture series. So thank you and all the best.